Okay, it's time for more on object-oriented programming. There are still quite a few important object-oriented programming concepts that we need to introduce. And the best way to do that, as you've heard us say many times, is through examples. But instead of introducing a new application, we're going to keep working on the example that we've already introduced, our doubly linked list. A small difference is that we're going to use an installed version of MATLAB to do it, revision 2020A. MATLAB Online is currently also running revision 2020A, so the results will be the same. So, we're going to do more. What more can we do to our doubly linked list? Well, the first thing we're going to do is change the order in which the items are inserted on the list. Our dlist class in the previous lecture stores data in the order in which we insert them. When we insert a new element, it goes at the end of the list. For some users, that's fine, but for others, a sorted list would be better. So let's create a new class called OrderedList that will insert items in increasing order. While that sounds easy enough, there is one conceptual difficulty. Our linked node class doesn't actually store any data. Only its subclasses do that. Each subclass will decide what kind of data to store, and the kind of data determines what sorting really means. For example, the method of determining the order of numbers would be different from the method of determining the order of strings. In other words, when we want to insert a node into the item list, we'll need to compare the new item with the existing items already in the list to be able to decide the proper location, and the comparison method will be different. So how can we implement our ordered list and our linked node in a general way so that insertion will work for any subclass that we may add later? Well, object-oriented programming offers an elegant solution called operator overloading. What that fancy expression means is that for any class, we can redefine what existing operators do when applied to instances of that class. For sorting, we need to redefine the relational operators, like less than, equal to, and greater than. Confused? Well, that's because we haven't shown you an example. Let's cure that confusion with a quick addition to the linked node class. We're going to add another methods section. I'm going to give it an attribute that we haven't used before. The first thing to note is that a class definition can include multiple methods sections. It can also have multiple property sections, and each one starts with the methods or properties keyword and ends with the end keyword. The second thing to note is that you can assign an attribute to methods sections. In this case, the attribute is a new one called abstract. You can have different attributes like abstract and private for different sections, and there's no limit on how many methods or property sections a class can have. We'll explain what abstract means in a minute or two, but the third thing that you need to know is that the name of this method, which is GT, is the same as the name of a built-in MATLAB function. That built-in GT is MATLAB's greater than function, and it returns true if and only if its first argument is greater than its second argument. The cool thing that we're going to take advantage of is, though, that the built-in GT function is called whenever you use the greater than operator. Like this. So when MATLAB sees this operation, it calls the built-in function GT with the first and second arguments being 6 and 5, like this. Why is that cool, and how can we take advantage of it? Well, we can take advantage of it because if you define a method named GT in a class, then MATLAB will invoke that method instead of the built-in GT function whenever you compare two objects of that class with the greater than operator. And that's called operator overloading. To be specific, defining a method to redefine a built-in function for specific classes of input arguments is called overloading. And when that function is the implementation of an operator, like the greater than sign, it's called operator overloading. Oh yeah, and it's cool because I say it's cool. We'll demonstrate operator overloading in a minute, But first, let's get back to that abstract attribute. You can assign the abstract attribute to methods, as we have here, for example, or to properties, or to classes themselves. What does it mean? Well, remember that we don't want anybody to create an instance of the linked node class. Instead, we want to restrict them to creating instances only of subclasses of linked node. Well, we can enforce that restriction by marking the linked node class as being abstract. And we can do that in three ways. First, by including the abstract attribute in the heading of the class definition. Second, by making any of its methods sections abstract. And third, by making any of its properties sections abstract. And once a class is marked abstract, you can't create any instances of it. It's not allowed. It causes red things to happen. Well, let's try it anyway. Told you. Furthermore, if you define a subclass of a class with any abstract methods or properties, then that subclass will also be an abstract class with no instances allowed, unless it includes a concrete implementation of every abstract method and every abstract property in its superclass, where concrete means non-abstract. So what is an implementation? Well, for a method, an implementation is a function definition. With the function keyword and a function signature with the same name as the abstract method, and a function body, just like all the methods and the functions that we've ever seen before in this course and the course before this one. But what we've got here is a method with a signature and no implementation. And that's good because an abstract method can't have an implementation. Oh, and a concrete implementation of an abstract property is just a property with the same name that's not declared to be abstract. But why did we particularly make the method GTAbstract? Because linked node does not contain any data, so we cannot possibly implement GT inside it. Of course, we could just leave GT out of linked node entirely, since it's of no use to linked node. But we want to ensure that every subclass of linked node does have a GT inside it, so that it's possible to compare nodes of those subclasses to maintain an ordered list. And guess what? We have ensured just that right here, by including the signature of GT in an abstract methods section. Now, if we fail to include an implementation of GT in a subclass and then try to define an object of that subclass, MATLAB will get mad, and MATLAB will get red. Okay, we need an example to make all these abstract ideas concrete. Let me stop right there. I ordinarily don't approve of puns, but make all these abstract ideas concrete? Well, that is primo, first class punmanship right there, folks. First class. So let's get to our example. For the sake of simplicity, let's make it a subclass of linked node that contains just a single number and call it sorted number. Our new class adds a new property called value to the properties that it already inherits from linked node, which are next, prev, and owner. This property is where we're going to store the data for sorted number nodes, and we're leaving it public because there's no reason to hide it from the user. It also adds two new methods, a constructor and a method with the same name GT as the abstract method that we defined in the superclass. This method provides the implementation of the abstract method in the superclass that we were just talking about, so we can create sorted number objects. But first, we're going to spend some time on this constructor, which takes just one input argument. We restrict that argument to be a scalar and to be numeric, and then assign it to the value property. We restrict it to be scalar because we want to keep the values in order, and it's not so clear how to sort multi-element arrays. We restrict the value to be numeric because, well, look at the name of the class. To impose these two restrictions, we've used an if statement and the isScalar and isNumeric functions. We've done this sort of thing whenever we've needed to restrict a function's inputs, but recently MATLAB has added a better way to impose restrictions on input arguments. Let's use it. What we've done here is replace our if statement with these 3 lines. This is a brandy new feature of MATLAB introduced last year in 2019B with a brandy new keyword, arguments. Adding a new keyword to the language is a big deal because even with this new one, there are still only 25 keywords living in the entire vast kingdom of MATLAB. And by keyword, I mean a word defined by the language to have a special meaning, better known as a blue word, because MATLAB paints its keywords blue. 20 of these blue words are also reserved words, meaning that you can't use them as variables or function names. That's why you'll never have a MATLAB function named, well, say function. But the arguments keyword is not reserved, so you could define a function named arguments. You can even name an argument arguments, but I can't think of any good arguments for naming arguments arguments. This new keyword is used to delimit a so-called arguments block, which starts with arguments and ends with end. And the arguments block implements the new feature, which is called function argument validation, or just argument validation, or even just validation. Before we get into argument validation, though, I want to urge you to pay close attention to it, even if your version of MATLAB doesn't have it. And that's because later in this lecture, you're going to learn that another kind of validation that's been around since 2017 uses exactly the same ideas and almost exactly the same syntax to check property values. In fact, that's why now, in the middle of object-oriented programming, is a good time to introduce argument validation, instead of in our lesson on functions. That's right, it works for normal functions too. So let's look more closely at this arguments block. First off, arguments blocks must come before anything else in the body of the function. Second, an arguments block must include one line for every formal argument in the function's signature. Third, each line must start with the name of the formal argument. And fourth, the arguments lines must be in the same order as the arguments list. On a given line, after the name of the formal argument, you can include optional so-called qualifiers, each of which restricts in some way the value of that argument, which of course is not known until the function is called with actual arguments. MATLAB highlights the qualifiers in this brown shade here. This particular function has only one input argument, so there's only one line in the arguments block. Our first one gives the required size, in this case 1 by 1, in parentheses. And you can use the colon to allow any number for a given dimension. Our second qualifier is a list in braces of so-called validation functions. In this case, we include only one validation function, and it's pretty clear what its restriction is: must be numeric. You can look up argument validation functions in the documentation up here to get a list of the validation functions you can choose from, and you can even define your own. Between the size and the list of validation functions, you can specify a class which restricts the input to be that specified class, or a class that can be converted into the specified class. So, for example, if we specified the class double, then an input that's an int 8 would be okay, because an int 8 can be converted to a double. If it can't be converted, or if any of the restrictions are violated, then a red error is thrown and execution halts. Finally, you can add a default value at the end of the line, which is used if the actual argument is omitted. The syntax is simple, an equal sign followed by the desired value. We've given 0 as the default, and you can see that its color is black instead of brown. I guess that's to make it look more like an ordinary assignment statement. The order that we've given, variable name, size, type, list of validation functions, and default values required, but you can leave any or all of the qualifiers out as long as you don't leave out the argument's name. There are a few more wrinkles that we haven't mentioned. For example, in the size restriction qualifier, if the input has smaller dimensions than the specified shape but can be expanded to the specified shape by duplicating elements, it will be expanded instead of throwing an error. So, for example, if you specify a 5-element row vector, but the input is the number 3, it will be expanded to a row vector containing 5 3s. Also, argument validation can't be used in abstract methods or in nested functions. You can look up arguments in the documentation for more details, but I've told you just about everything you need for 99% of the cases you'll run into. Okay, now that you know this new way to validate arguments, we're done with the constructor. So let's look at that method GT. As we mentioned, this is an implementation of the abstract GT in the superclass link node. As we said, it's important that this implementation be included in sorted number. Otherwise, sorted number will be an abstract class, just like its superclass, because it inherits an abstract GT, and any class with an abstract method is an abstract class. And as we've also said, we don't want that because you can't use an abstract class to make objects. GT takes 2 nodes as arguments, which will both be objects of the class sorted number, and compares their value properties to determine whether the first one is greater than the second one, and puts the result, which is true or false, into the output argument res, R-E-S, which is an abbreviation for result. By the way, we can now see why we restricted the value property to be scalar in the constructor. It's so that when we compare the 2 value properties here with the greater than operator, we're guaranteed to be comparing scalars. Let's test it. I've made a live script to make it easy. Let's see, 3 is greater than 4? No, and we get false, correct. Is 4 greater than 3? Yep, and we get true, also correct. Seems to be working. But how can we know for sure that it's actually using our new method instead of the built-in greater than function? In other words, how do we make sure that we've actually overloaded the greater than operator for this class? Well, let's put in a breakpoint and try the first one again. Well, this little green arrow tells us that we are indeed running inside the GT method. So finally, after that long detour into argument validation, we know for sure that operator overloading actually works. And I repeat, this is cool. Okay, very cool. So folks, we have hacked the greater than operation and diverted the system into our code where we can do what we want to do. This is a good hack, not a bad one. We could do damage to unsuspecting users if we were bad hackers, but we're not. We're the good guys. Okay, let's remove the breakpoint. And let's see what happens if we use an operator that we haven't overloaded. Let's try the less than operator. Well, it didn't throw an error, so that's good, I guess. But what about the answers? Instead of checking them, let's just run it a few more times. Well, the answers are changing even though the operands aren't changing. So it certainly does not work correctly. So what's going on? Well, since we haven't implemented our own less than operator for the sorted number class, MATLAB has no idea that it's supposed to compare the value properties of the operands. How could it? Instead, it uses a special built-in default function defined for the handle class. It's not important to us to know how it works, so we won't cover it here. You can read the MATLAB documentation if you like, but the important thing to remember is that while it won't throw an error, if you want to use any of the relational operators on your class, you need to overload them. So let's go ahead and implement all the rest of the relational operators for sorted number. We'll first define abstract methods for all 6 of them in link node. Greater than or equal, less than or equal, and not equal. And now let's add methods to implement them in the sorted number class itself. There they are, all 6 of them. And let's test them with this script, which compares the results of the overloaded operators on sorted number operands with the built-in operators on corresponding numeric operands. If the overloaded operators are working, we should get a result of true for every comparison. Every result is true, so it passes every test. And we've got all the overloaded operators working for sorted number. So we built the class we need for our nodes. Now let's link them into a sorted list. We need to define a class for a sorted list. Let's call it OrderedList instead of sorted list, just so you'll know you don't have to use the same name for the list and for the nodes. And we'll put sorted numbers on the list for our example. But we could put other classes of nodes on it too. And we'll do exactly that in our next lecture. We want it to be a doubly linked list. And we've already implemented a doubly linked list named dlist. So we can use dlist, which we've already debugged and tested, to build OrderedList by making OrderedList a subclass of dlist. We're following one of the tenets of object-oriented programming, which says that we should reuse things that we've already built as building blocks for new things. That saves a lot of work. But there's still some work to be done because while almost everything in dlist will work for an ordered list, the insert function will not work. That function always inserts the node we give it at the end of the list. But we want to insert the node at just the right place so that the list is kept in increasing order. So here's what the class definition for ordered list looks like. Like any subclass, it inherits the properties and methods of its superclass. But we've overloaded the insert method with a new version that keeps the nodes sorted. Actually, we should say that we have overridden the insert method because, well, object-oriented people say override instead of overload when the function that you are redefining is a method in a superclass. We don't have time for a line-by-line explanation of this method. Of course, we'd find time if it were necessary, but the inner workings of the insert method are not all that important for understanding object-oriented programming, so we won't. The important thing is that it inserts a node in the proper place in a sorted list. However, to help you when you do delve into it, we'll make a few remarks. The most important remark is that the while loop here determines where to insert the new node in order to keep the values in increasing order. Another remark is that the cur and prev pointers track the current node and its previous node as the loop traverses the list, comparing the node to be inserted with each current node. The next remark is that the node greater than cur comparison here invokes the GT method of the sorted number class that we added to that class a few minutes ago. And the final remark is that when the loop finds the right place in the list, it inserts the item between prev and cur. So what have we done so far to get an ordered list? Well, we just now created a doubly linked list named OrderedList by making it a subclass of the superclass dlist. And we overrode the insert method. And before we did that, we created a node subclass named sorted number based on the superclass linked node. You may remember that we made the properties of a linked node semi-private instead of private by giving dlist explicit access. Right here. What we didn't mention, though, is that this listing not only gives dlist access to these properties, but also gives automatic access to any subclasses that dlist might have, which means that we don't need to add the OrderedList class to this access list. It gets access automatically just by being a subclass of dlist. There is one superclass change we need to make, though, and it's in dlist. Let's look at the access attribute for the properties in dlist. We've set it to private, which means that only D-list objects can see them. That won't work for us because our ordered list objects need to use these properties too, and private properties are not accessible to subclasses. We could, of course, just change the access to public, but we don't need to do anything that drastic. Fortunately, there's a middle ground, and it's called protected. Let's change the access attribute from private to protected. This change extends the access to all subclasses of D-list, so now OrderedList can access the properties of linked node and D-list just by virtue of the fact that it's a subclass of D-list. Let's see how all this works now using this live script. First, we define 3 node objects, X, Y, and Z. Next, we create a list and insert these nodes into that list, but not in order. And now we look at the list to see whether they were inserted in proper order. Yes, they were. And let's insert some nodes directly and take another look. All working as expected. Let's see if we can break it. Let's reach in and change the value of one of the nodes that's already on the list. And take a look at the list now. Well, we broke it because X is still right here where it was on the list when we inserted it before, instead of being shifted to its rightful place, which is now at the tail. Let's add code that will move it to the right place if its value is changed. It might seem that we would need to add the code to OrderedList, since the list is going to have to be changed, but the trigger that causes the change has to be in sorted number, because we're directly accessing sorted number to change its value property. So we'll put the trigger in sorted number and call methods in OrderedList from there. The trigger is a setAccess method which MATLAB calls automatically when the user assigns something to the value property. We introduced the setAccess method in our previous lecture, and here's what the one we need looks like. Do you remember the syntax for the setAccess method from our previous lecture? You name the method set, followed by the dot, followed by the property name, which in this case is value. And this method will get called the next time we assign something to the value property of a sorted number object like, say, X. The method starts by validating the argument in exactly the same way that the constructor does to make sure that it's a numeric scalar. Then, if the object is not already in some list, that is, its owner property is empty, we can safely change the value without further ado. However, if the object is already in a list, we remove it from that list, change its value property, and then insert it back into that same list. You may be wondering why we save the owner property in the local variable list right here. Well, we save it because when the remove method removes the node from the list, it also sets the owner property to the empty array. We have to save the owner so we can use it to call insert. That should do it, but I'm having a weird premonition that I'm going to be talking about another access problem in just a few seconds. It's like I almost know what's going to happen before it happens. Strange. Let's repeat what we were just doing in the live script. We set the value property of X to 1,000 and then looked at the list to see if it was still sorted. Okay, set the value property. Oops, no public property owner. So what do we do just now to cause this error? We added that setAccess method to sorted number, and it does use owner. We were just talking about that, and here's sorted number complaining that it can't access owner. Man, I thought we had all these access problems solved. And there you go. My weird premonition was right on target. Here I'm talking about another access problem. I'm creeping myself out here. Man, if I could use this with a stock market. But back to business. Where is that owner property that sorted number can't access? You might remember where it is because we looked at linked nodes properties a little while ago. And that's where owner is. Let's take another look. Yeah, these properties are semi-private, meaning that they're hidden from all classes except those in the access list, which right now includes only DList. But as we pointed out already, when you put a class on the access list, its subclasses automatically get access too. So OrderedList, which is a subclass of DList, has access to them. But nothing else gets access, not even the subclass of linked node itself. So sorted number is outside the privacy fence, trying to peek in to access owner, and that's why we got the error. So what's the solution? I'm sure you've noticed by now that in this perfect video world that I live in, there's always a solution. It's like a romance novel, without the romance. Of course, one simple solution is to simply add sorted number to the list of classes that are granted access. That would solve the problem immediately. But then, if at some later time we needed to declare another class to be a subclass of linked node and give it access to these properties, we'd have to open up the linked node class definition like we've done here and do surgery again. That goes against the object-oriented programming philosophy, which, as we've already said, requires that we be able to use things that we've already built, tested, and debugged as building blocks to build new things without having to change the originals and risk introducing new bugs. Fortunately, there's a solution. It's a little wacky, but it's a solution. I actually hinted at this solution a minute ago when I repeated that, well, just listen to it again, which right now includes only DList. But as we pointed out already, when you put a class on the access list, its subclasses automatically get access too. So OrderedList, which is a subclass of DList, that's the hint. Can you figure out what to do? Well, and this is going to sound a little wacko at first, what if we added linked node itself to its own access list? Like this. Of course, linked node already has access to its own properties, so it might seem like a waste of precious keystrokes to put it on its own list. But if you think about this a few seconds, you'll realize that now all subclasses of linked node, including sorted number, and any other subclass we might add in the future, have access to these properties too. That's the weird, wacko, crazy solution to the problem. Well, let's see whether this cockamamie scheme works by repeating the value change a third time. 3's a charm. We changed the value of a node that's already on the list, didn't get an error when the setAccess method accessed owner, and when we check the list, we find that 1000 is at the end where it belongs. Well, there you go. Our kooky, harebrained, daffy scheme of adding a class to its own access list turns out not to be so daffy, harebrained, kooky, wacko, or weird after all. Well, weird maybe, but not all that other stuff. We started with semi-private access, in which a class grants access only to listed classes and their subclasses, and used a scheme to change the access to what you might call semi-protected, in which a class's properties are accessible not only to the set of listed classes and their subclasses, but also to all its own subclasses as well. I told you object-oriented program was tricky, didn't I? Oh, no? Well, maybe I didn't. But I'm telling you now, and weird or not, you need to keep this trick handy. So we've created a sorted number class and an ordered list class. And we've added sorted number objects like X, Y, and Z to the ordered list object MyList. And we even changed the value of an object that was already on MyList while keeping the list in ascending order. That's great. But suppose we want to remove, say, Y from the list. How would you do that? We need to define a method that will delete an object from a list. To get ready for that, we need to show you something with this live script. First, we'll start over with a fresh, empty MyList. Then we define some sorted numbers, insert them into MyList, and display it. Next, we define a couple of normal variables of class double and run whos to look at the workspace. As you can see, the number of bytes shown for each of our objects is 8. It might seem odd that MyList and X require the same number of bytes in a workspace, even though clearly MyList requires much more memory space than X. That's because OrderedList and SortedNumber are handle classes. As we explained in the previous lecture, when you define a handle object, the only thing that's stored in the workspace is a pointer, and that occupies only 8 bytes. It points to the handle object, which holds all the object's data, and that data is stored in another section of the memory. In the class column, you can see that MATLAB treats OrderedList and SortedNumber no differently from double. They're just two more MATLAB classes. They aren't built-in classes like double, but they are on an equal footing with the built-in types. I included the complex number to show you what the attribute column is. Other attributes are global, persistent, and sparse, but handle is not an attribute. Now let's execute these two commands, xdelete and whos again. First of all, where did this delete method come from? We haven't defined it yet. Well, it's a built-in method for handle classes, and since SortedNumber is a subclass of linkNode, which is a subclass of the handle class, the handle object X, which is an instance of SortedNumber, can use it. The delete method is known as a handle class destructor, or just Destructor, and it clears the handle object and its handle from the memory, recycling their memory cells for reuse and thus saving the planet. However, as you can see from the whos command, X is still there in the workspace. This delete method doesn't clear variables from the workspace, that's the job of the clear command, but it does delete the handle from X, and that's why X's value now occupies 0 bytes, just like an empty array. This 0-byte object of the SortedNumber class denotes a handle to a deleted sorted number, and MATLAB will tell you exactly that if you ask it what's in X. So what does deleting a node that's linked into MyList do to MyList? Well, let's display MyList. What happened here is that DisplayList printed just the first item on the list with the disp function, which announced that it was a handle to a deleted sorted number, and so far no error. But then, when DisplayList tried to use the next property of this deleted item to go to the next item on the list, there was no next property, and that caused the error. So we've succeeded in deleting an item from our list, all right, but we've also succeeded in fouling our next and have therefore ruined our list. This error shows that MATLAB's handle class destructor is not the right way to remove an item from a list. We need to do what we set out to do, which is to define our own delete method, which will override the built-in method, and when we write it, we'll make sure that it won't ruin any lists. But instead of putting it in SortedNumber, let's override it in linkNode, so it'll be available not only for SortedNumber, but for any other subclasses of linkNode that we might define. And before we put that delete function in linkNode, I should point out that there are a few requirements for a proper delete function. It can have only one input argument, which is the object that it's deleting. It can't have any output arguments. It can't include an arguments block for validating the input, and it can't be declared abstract. You can look up handle class destructor in the documentation to get more details. So what should our destructor do? Well, that one's easy. It's easy because we've already written a remove function that will remove an object from a list. So all this destructor has to do is call remove. And here's what it looks like. One if statement is all it takes. That if statement checks to see whether the node has an owner. If it does, then that means that the node is linked into a list and it needs to be unlinked from that list. To do that, delete calls the remove method to do the unlinking. Unlinking just changes some prev and next pointers. It doesn't actually delete anything from the memory. And if the node doesn't have an owner, then it's not on any list, so our little destructor does nothing at all. But whether this destructor does anything or not, the mere fact that a destructor was called will cause some serious action behind the scenes. MATLAB will note that the destructor was called, wait for the destructor to return, and then immediately, without fanfare, run the handle class destructor to clear the object from the memory and make the space available again. It's important that MATLAB be vigilant about removing handle objects, because otherwise a program could generate millions of them with pointers to each of them and then begin deleting the pointers, in which case it would become impossible to access them. And if MATLAB didn't reclaim the space, the memory that's available for new objects would get smaller and smaller until there's no available space left. When that happens, the next attempt to allocate a new object or any new variable will cause the program, and quite possibly MATLAB itself, to crash. It's as if the memory were leaking right out of the computer. And in fact, such occurrences are called memory leaks and are a problem in some systems. To avoid memory leaks, MATLAB continuously monitors the links to handle objects. And when the last link to a given object is removed, MATLAB calls its delete method and reclaims the space. Let's look at a very simple example of this reclamation in action. First, let's put a breakpoint in our delete method. Now let's run this live script. First, we assign X a handle to a sorted number object. Then we copy that handle into Y and Z. So now we have 3 pointers to the same object. Next, we clear X. So there are only 2 pointers left. Next, we clear Y. So now there's only 1 pointer left to the object. And finally, we clear Z, which removes the last pointer. At that point, MATLAB detects that there are no handles left pointing to the object, which means that there is no access to it, which means that the memory space that it occupies can't be accessed by any other objects and is therefore useless. So it automatically calls the delete method for the object's class. And here we are at the breakpoint. We can hit continue and let it finish. Of course, our delete method doesn't do anything for this object because we never put it on a linked list, so it has no owner. But as soon as that method returns, MATLAB does what it always does when a class's destructor returns. It calls its built-in handle class destructor to reclaim the space. You can't see that call, and you can't see the objects disappear by looking at that workspace because handle objects aren't stored in the workspace. But rest assured that its memory has been reclaimed. And using clear is not the only way to remove a pointer stored in a variable. Assigning a new value to a variable that was pointing at a handle object removes that pointer. And if that was the last pointer to that object, MATLAB will call delete then too. I'm telling you, MATLAB is vigilant when it comes to memory leaks. Okay, let's remove our breakpoint. In this example, there was no need for our destructor. If we hadn't provided one, MATLAB would still have called the handle class destructor to get rid of the object. In general, if you know that no harm will come from deleting the objects to some class without first doing some housekeeping, then you don't need to write a destructor to do that housekeeping. MATLAB's built-in handle class destructor will handle all your destruction needs. But since our linked node objects are intended to be pointed at by prev and next pointers on a linked list, it definitely needs some housekeeping. so it definitely needs a destructor. And speaking of the linked list, what if we delete that? What should happen to the nodes on that list? Well, at the very least, their owner properties should be reset to the empty array since the owner no longer exists. Also, the next and prev handles of all the nodes on the list should be reset to the empty array too, because those nodes are no longer part of a valid list. Depending on how the nodes were created, if the list that they're on is deleted, then there may be no handle variables left in the workspace to refer to them. So one option is to just delete the entire collection of nodes on a list when that list is being deleted. If some handles outside the list refer to one of those nodes, like say the variable x in our previous example, then its handle will refer to a deleted object. And that may or may not be a problem. Another option is to merely delete the list object, set the owner properties of the nodes to the empty array, and otherwise leave the collection of nodes alone. In that case, the ever-vigilant MATLAB will determine which of those nodes can't be accessed by handles from outside the collection, and it'll get rid of them. That avoids the problem of having variables pointing at deleted nodes, but it doesn't reclaim as much space. There's really no one-size-fits-all solution. But whatever you decide to do when you write your own classes, your documentation, or at least comments in your code, should state their behavior, including what happens with deletions. Well, let's write the list destructor. And let's take the approach of removing the nodes so that you can see how it's done. As we will see, our destructor will work not only for the ordered list, but also for any D list. So we'll put it in D list and let OrderedList inherit it. Before we look at the algorithm that this method uses, which comprises just one while loop, I want to point out something very important. Even though we have a function named delete calling a function named delete in object-oriented programming, this is not necessarily a recursive call, because even with the same names, these can be two different functions. The delete function, whose definition we're looking at here, is clearly a method belonging to the class dlist, but what about the delete that it's calling? What class does it belong to? Well, let's look at that function call. The call uses the dot operator twice, and the syntax of the dot operator requires that its left operand be either a struct or an object. In this application, of course, it's an object, and therefore its right operand must be either a property or a method defined in the class of that object. To put it less legalistically, each dot has an object on the left and a property or method on the right. So let's look at each of these two dot operations. For the first one here, the left operand is list, which is an object of the class dlist, and the right operand is a property of that class called head. The output of that operation is whatever object is stored in head. So now we can look at the second dot operator. On the left it has the object stored in head, and on the right it has the method named delete, which must be a method defined in the class of head. So unless head is a dlist object, the delete that's being called is different from the delete that's doing the calling. And if they're different, it's not recursive. So what is the class of the object stored in head? Well, there's no way to tell by looking at this code. It depends on the class of the object that we inserted into the list. If its class is linked node or letter node or sorted number, then this is not a recursive call. But if its class is dlist or OrderedList, then it is a recursive call. In this second case, it means that one of the nodes on our list must itself be a list. There's nothing inherently wrong with either of these things. A recursive call is perfectly fine, and so is having a list on a list. Of course, if list is going to be a node on a list, the class of that list node needs to have everything required of a node on a list. So, for example, you'd have to add things like next, prev, and owner to dlist in order to put it on a list. But if you did that, then you could have a list on a list. And the recursion aspect would be no problem. Recursive methods work just like normal functions, perfectly legal, perfectly fine. So now let's look at this algorithm. Its goal is to delink the nodes in the list. and it does it with a while loop that repeatedly deletes the head. Well, your first reaction might be to ask, how could this possibly work? We repeatedly delete the head of the list? But there's only one head, right? Well, yeah, there's only one head at a given time, but when we delete the head of a list, the item that was second on the list now becomes the new head. That's taken care of by the remove method, which is called by the delete method that we just added to link node a few minutes ago. So removing the head over and over will in fact remove node after node until no nodes are left, at which time head will be the empty array. That stops the loop and the method returns. Pretty clever, isn't it? So delete has delinked all the nodes from the list object, but the list object is still sitting there in the memory. Sitting there for a microsecond or two, that is, because as soon as delete returns, MATLAB stealthily calls its built-in handle class Destructor on that list object, reclaims the space, and that list object is no more. And although I didn't mention it, after each call to the node's delete function, MATLAB stealthily calls its handle class Destructor for that node, and it's bye-bye node. So in the end, it's killed the list and everything in it. It's a massacre. Okay, enough talk. Let's try it out with another live script. We start by assigning a new ordered list to MyList. Then we get a handle to a sorted number with the value 10 and assign that to X. Then we insert the object pointed at by X and a few other sorted number nodes into MyList and display it. And there they are, 4 items on MyList. And now we delete the list and then ask MATLAB what's in MyList and what's in X. And it tells us that these variables hold handles to deleted objects. So our delete function has in fact deleted MyList and all the nodes that were on it. As we noted earlier, this approach of deleting all the nodes on the list can cause some variables to point at deleted nodes, but it does reclaim the maximum memory. All right, we're almost done with our sorted number list implementation, but let's make a few improvements. First, I don't much like the way we're displaying our list. You can see it here in our live script. There are 2 improvements I'd like to make. First, I'd like to change the name of display list to disp, because disp is the name of MATLAB's built-in display function, so the user is more likely to remember that name than display list. In other words, we're going to overload the built-in disp function. Second, I like to show just the values of each node instead of repeating sorted number with properties over and over. Let's start with the first improvement, which just changes the name. We define display list in dlist, way down here at the bottom. It uses a while loop to go through the list and uses the built-in function disp to display each node. Let's change the name of the display list method to disp. You've probably noticed that I often put empty parentheses on methods whose only argument is the object to the left of the dot operator. It's not necessary, but I do it to let the reader know that this is a method and not a property. This disp is here to display the object in item, and we'll overload disp in sorted number to make it print out only the value property of the object. But before we do that, let's override disp in ordered lists by adding just one line to display a heading. Okay, let's try that out. So we've changed our method name from display list to disp, and we've added the heading ordered list containing. Now we need to overload the disp function for sorted number. We've defined link node too, but it's an abstract class, so we can't define link node objects. We'll give it an abstract disp, which ensures that any subclass must have a disp implementation, and then implement disp in sorted number. Here's LinkNode's new abstract method to overload DISP. Right here. And here's the implementation of that method in sorted number down here at the bottom. Pretty underwhelming, isn't it? All it does is hand the node's value property to the built-in DISP. And this is also not a recursive call because the node's value property is not a sorted number. It's just a number. Ah, that's what I wanted to see. And we've got only one quick thing left to do in this lecture, and that's to improve the validation technique that we used in sorted number. Do you remember how we validated input arguments in its constructor and in its setAccess method? Just look for the brown color. In each of these two methods, we used an arguments block, here and here, to validate that an input argument is a scalar and it's numeric. We checked the variable n here in the constructor, and we checked new value here in the setAccess method. We did all that checking because each of these two methods assigns the input to the sorted number's value property. This approach works, but there's an easier way. It's called property validation, and unlike argument validation, which was born in 2019, property validation is 3 years old, which is a long time in programming years. So you're more likely to have it if you're using an installed version. Oh, and here are a couple notes for people watching me in the year 2050. First, installed means actually running on the machine you're using. People used to do that. You can look it up in any history of computers. And second, you need to find yourself some new videos. Anyway, with property validation available, we don't need no stinking argument validation. Instead of using argument validation for every input argument that's assigned to any property, we just validate the property itself one time, like this. Boom, done. And that's the name of that tune. The syntax and semantics are identical to that of one line in an arguments block, like the ones that we put in the two methods. So you've already learned it. Even the colors are the same. Since we're validating value in the properties block, I've removed all the qualifiers from the arguments block in the constructor, but I've left the default value assignment, which we need in case the user omits the argument. If your installation is earlier than 2019b, you can use the old-fashioned if nargn equals 0, n equals 0 technique. But we don't need a default value for the setAccess method because when it's called, the argument is provided automatically, so I've eliminated its arguments block entirely. Let's assign some valid and invalid numbers to sorted number to check its property validation, which will also give us a chance to see how its DISP method works when we call it directly instead of having the DISP in OrderedList call it. First, we'll use a valid number input to define a sorted number object. What happened here is that, as usual, when we leave off a semicolon from an assignment statement, MATLAB prints out the name of the variable receiving the assignment and an equal sign, and then calls DISP to display its value. Since we overloaded DISP for objects of type sorted number, it calls our overloaded version, which displays the value property, so we get A equals 8,645, which is just exactly what we want. Now we'll call A's DISP method directly. And again we see what we want. It's working perfectly with valid inputs. Now let's try a value that should be invalid. We'll give it a string instead of a number. Looks like MATLAB takes issue with that. And let's try another no-no, a vector. And MATLAB objects strenuously to having that second 4. Well, it's not often that I consider an error to be good news. Almost never 2 errors in a row, but this is good news because we wanted our property validation to throw an error for these 2 cases, and it did. So we got errors when we wanted them and no errors when we didn't. We are totally on the same page with MATLAB. One thing to note about property validation that we haven't demonstrated is that if you change the property validation while objects of the class exist, MATLAB doesn't apply the new validation to those objects until you attempt to assign new values to their properties. And there are a few more details about property validation that we don't have time to cover, but they're all there in the documentation. So, we are done with sorted number. Or more accurately, I'm done. There's still a number of useful methods that we should add. For example, it would be nice to be able to determine whether a certain number is on the list or not. We'll leave that as an exercise for you. As you'll see, your assignments will ask you to extend our fine classes to make them even finer. Before we end the lecture, though, let's summarize the things we've learned. First, we learned how to overload an operator using greater than as our example, and I have deemed that to be very cool. We learned how to declare methods to be abstract, and that a class with even one abstract method cannot be used to define objects. But we also learned how to implement its abstract methods in its subclasses so that those subclasses can be used to define objects. We learned how to validate function arguments, and we just learned how to validate properties. We learned that an access list, which we introduced in our previous lecture to allow listed classes to access private properties, extends access also to the subclasses of those on the list. And we learned a wild and crazy trick that takes advantage of that to extend access to subclasses of the class itself. We learned about the protected access attribute, which extends access of the properties and methods of a class to its subclasses, but hides them from all other classes. We learned about handle class destructors, which tidy up when we're done with handle objects, and we learned that MATLAB recycles the object's memory when they're no longer reachable via any handles and are therefore no longer usable. Its constant recycling avoids so-called memory leaks, when more and more memory is occupied by inaccessible objects. So we're ending another lecture, and here again we've learned a lot, but here again we're not done. But don't go away. You'll want to stick around for the next and final episode of our exciting object-oriented serial. It's called Tying It All Together. And believe you me, it is a real stem winder.